In week 1, we are going to look at electrical quantities and basic circuits. We'll answer what is a circuit and how do engineers describe it. By the end of this week, you should be able to define voltage, current, resistance, and power. Apply Ohm's law to simple circuits. Explain the difference between series and parallel connections. Identify nodes, branches, and loops. Apply Kirchhoff current law. Apply Kirchhoff voltage law. Explain the relations between resistance and resistivity. Analyze simple resistant networks using circuit topology and equivalent resistance. This diagram shows a specific type of information in the physical world is detected by the sensor, which convert this information to electrical signal. The computer then calculates and then make decisions based on the program. The decision as electrical signal will be received by the transducer. The transducer will then alter the condition of the outside world. In this typical engineering system, mechanical engineer, they are interested in the transducer. It means the mechanical part of this system. Electrical and electronic engineer, they are interested in the electrical part, how the signal transfer, and how to convert the physical signal into the electrical signal. The computing engineer, of course, they want to focus on the computing system, it means the software part. Mechatronic engineer, they will look at this system as a whole and try to optimize all the process. While civil engineer also play an important role, because civil engineer, they need to understand in future how to build smart infrastructure using adaptive and dynamic system. A thermistor will convert the temperature into voltage. A potentiometer will convert the position of an object into voltage. And strain gauge will convert the force into voltage again. And the LDR, the light dependence resistor, will convert light into voltage. Here I want to give one example of a sensor used in everyday life. What physical quantity does it measure? Let's look at some fundamental electrical quantities. Voltage represents the change in electrical potential energy or work done per unit charge. So the defining equation, the equation which defines voltage, is equal to delta W, the change in electrical potential energy or work done over charge. So the unit for voltage is volt and the symbol is V. However, if we reduce this unit into back to the base SI unit, you can see it is kg meter square over coulomb dot second square. Electric current represents the flow of electric charge per unit time. So the defining equation is I equal to delta Q, how much electric charge flow passing through a point in the circuit, and how long it takes. So it's the number of electric charge per second. The unit of current is ampere, and the symbol is A. And if you reduce this one back to its base SI unit, is coulomb per second. Resistance describes the opposite to current flow. So the defining equation is R equal to V over I. And this is the Ohm's law, of course. So the unit for resistance is ohm, and the symbol is omega. If we look at the unit and try to reduce this unit back to the base SI unit, we'll find the ohm actually it is kilogram times meter square over coulomb square times second. Power describes the rate of change in energy or the rate of energy transfer. And the defining equation P is equal to IV. Its unit is watt, W, and it is joule per second, or kilogram dot meter square over second cube. Voltage V is defined by this equation. V equal to W over Q. Sometimes people will say V equal to delta W, delta Q, and W itself is work done. When you move the charge within electric field from A to B, you have to perform work. So this is work done. Alternatively, this can represent the potential energy difference between A and B. A little bit like you drop the ball from here to here. The potential energy difference is mgh, but this time is electrical potential energy. And here, this is the gravitational potential energy. So the way we do this sort of problem is we ask if V is defined as W over Q, what is the unit of V, I mean the unit of voltage. So I will put a bracket here, and it means the unit of V, and it is equal to the unit of W. It means the potential energy or work done over the unit of charge. And this is equal to joule per coulomb. And the meaning of volt or electric potential, this is volt or electric potential is how much potential energy or how much work done you move the charge from A to B, but it's per unit charge. So if you have 3 joule from A to B required, but if you have 2 coulomb of charge, so the potential difference is 1.5 joule per coulomb, or 1.5 volt. Now, this retain the true physical meaning. However, sometimes we want to break down further about what it really means joule, and we want to break it down into fundamental unit. So think about joule is energy or work done, and you think about work done is you have a object here. You push the object by force and move this object to a distance d, and we know the work done is Fd. So the unit of work done is joule. So this is the unit of force, and this is unit of force multiply the unit of distance. So it's a Newton meter. Next, you want to know what is Newton. Newton comes from F equal to ma. So the unit of force is Newton, and the unit of m is kilogram. The unit of a acceleration is meter per second square. So we combine everything. So joule is Newton. Newton is kg meter per second square multiply meter. So the joule can be expressed as kilogram meter square over second square. So if we look at here, the unit of volt it can be expressed as joule per coulomb, and this is the unit immediate from the defining equation, how we define voltage. However, if you break it down further, it will become joule per coulomb. So this is joule per coulomb. Electric current is defined by this equation. I equal to how much charge passing through a point per unit time. So the unit of I, the current, is equal to the unit of charge over the unit of time. So this is coulomb per second. When someone measures the resistance of a resistor, they will measure the current flowing through the resistor and also measure the voltage across the resistor. So the resistance is defined as V over I. So this is the defining equation for resistance. And the unit of resistance is the unit of V over the unit of I. It means volt per ampere. Now, of course, we also use another one. This is ohm. Now, the ohm here, you can think of like a preferred name of the V over A. So you can say V over A, volt per ampere, or most of the people will say ohm. Next, we want to break it down. So let's see. V over A, if we further break down, V is joule per coulomb, as we learned in question number 1. Ampere is coulomb per second. So do the math. This is joule second over coulomb square. And you will remember joule itself is kg meter square second square. And then now this one, this is the joule, multiply second over coulomb square. So you got kg meter square over second over c square. And you can see the ohm can be reduced into kg coulomb square meter square over second. When a resistor connects to a power source, the power delivered to the resistor is equal to IV. So power P is defined by IV. The unit of power, therefore, equal to the unit of I multiply the unit of V, the voltage. The unit of I is coulomb per second, and the unit of V is joule per coulomb. So you can see the coulomb cancel out and you get joule per second, and the preferred name for this one is watt. Next, we can further break down the unit of joule. Remember, the unit of joule is actually equal to kg meter square second square. So the unit for power can be reduced to kg meter square over second square over second. It means kg, meter square, over second cube. We start from the Ohm's law, V equal to IR. So R equal to V over I, 12 volt over 0.5 ampere. So it is equal to 24 ohms. B, the power. Power is equal to I multiply V. It means 0.5 ampere multiply 12 volt equal to 6 watt. Let's look into what is electric current. From the defining equation, we say I, the electric current, is defined as the flow of electric charge per each unit of time. So this is coulomb per second. This is its unit, or we say ampere. Now this is a simple electric circuit. We have a battery connected to a light bulb. The electric current means we assume there's some charge. Now we know there's two types of charge. It can be positive or it can be negative. So in this picture, we assume some positive charge start from the positive terminal of the battery and move along the circuit. When the charge passing through the light bulb, it delivers its energy. It means it converts the energy from electrical, which carried by the charge, to heat and light. This charge, they won't disappear. They will return back to the negative terminal of the battery. Inside the battery, the chemical energy will convert into the electrical energy, and this energy again will carry by the electric charge, and it will start from the positive side of the battery and travel again. Now one thing is, because there are two types of charges, there are also a negative charge. So what scientists found, if negative charge start from the negative terminal and start here through the light bulb, return back to the positive, this negative charge will do the same thing. It means it will still convert the electrical energy into heat and light. Now, there's no way in this simple circuit we can tell whether this is a positive charge start from the positive, and or the negative charge start from the negative, because at the end of the day, what we really can see is the light bulb. It means some sort of electrical energy convert into heat and light. So we cannot tell. It means in all the practical senses, positive charge start from the positive terminal and flow through the circuit is equivalent to the negative charge start from the negative terminal and flow through the circuit. They produce the same effect. In reality, we know it is actually negative charge which carried by electron start from the other side, because we found each electron carries very little amount of charge. Say here should be 1.602 times 10 to the minus 19 coulomb. This is very tiny amount. So in order to carry 1 coulomb of charge, how many electrons you require? So this is easy. The number of electrons required to carry 1 coulomb of charge is 1 over 1.602 times 10 to the minus 19. And if you do the mathematics, this is equal to 6.24 times 10 to the 18. This is the number of electrons. So this is the simple circuit again. If we don't say anything, we always say I. This is the convention current. Start from the positive, flow to the light bulb, to the negative. And in reality, we know it's actually electron which carry negative charge and do it opposite direction. Let's have a look again. What is electric potential and electric potential energy? Now this is the battery again. And if you look at the battery, sometimes it will say 12 volt. Now V, this is electric potential. And we use the symbol V will represent electric potential. And we look at the defining equation. This is U. This is the potential energy or work done per charge. So this is Joule per Coulomb. Okay, so if we have a positive charge here, if this is positive charge here, the electric potential for the positive charge is 12 volt here, and at the other terminal is 0 volt. This is what you measure by a digital multimeter. So in this case, the potential difference between the negative terminal and the positive terminal is 12 volt minus 0 volt. So this is what we call PD. It means this is the difference between the 2 points. We have the different electric potential. So again, this is in V. And in this case is 12 volt. In a circuit, this say a battery here and here. If this is 12 volt, this can be 8 volt and this can be 0 volt. So you can say the absolute electric potential at the battery positive side is 12 volt. At this point is 8 volt. At this point is 0 volt. And the electric potential difference PD between the first resistor is 12 minus 8 volt. So the difference is 4 volt. And of course the difference between the 0 volt and here is 8 volt minus 0 volt is 8 volt. So this is the meaning of electric potential difference. Now let's look at energy. For the positive side, U is equal to QV. So here you have 12 volt and this is positive. For example, you have 1 coulomb of charge. So this is 1 coulomb. This 12 volt. And remember, volt is joule per coulomb. So you have 12 joule of energy. So when the positive charge starts from the positive terminal of a battery, it carries 12 joule per each coulomb. Of course, when it returns back to the zero, this 12 joule of energy will convert into heat or sound or mechanical or light. So it depends on how the electrical energy converts to other forms of energy. Let's look at negative charge. Assume we have negative charge. So negative charge start from here. Negative charge. Assume this is 1 coulomb. Again, if you ask what is the energy of this negative charge, so here U is QV. So in terms of energy, this is -1 coulomb. This is 0 volt. So this is 0 joule. However, when the negative charge moves along the path back to the positive side, let's calculate its energy. So at this point, for the negative charge, the energy U is QV, and Q is -1 coulomb because this is negative charge. V is positive 12 volt. You see the positive negative doesn't change, but the energy change because your charge is negative. So your energy become -12 joule. So what it means? It means for the negative charge, here the energy is 0 joule, but once it passes through here, the energy is -12 joule. It means the negative terminal for the negative charge still have higher energy when it compared with the positive terminal. So therefore, the negative charge will start from the negative terminal and move and convert its energy into other form. And of course, once it loses the energy, its energy becomes -12. Let's look at Ohm's law. If someone measures the potential difference across a resistor usually is made from conductor, and then you also measure the current passing through the resistor. And this is the voltage. Now you change the voltage and you look at the relations between the voltage across the resistor and the current passing through it. And now you plot this relation. So you will see when the voltage increases, the current also increases, vice versa. And if you put this in a mathematical formula, it will become V proportional to I. This one can be written as an equation. So V is equal to Ri. R is the proportional constant, and we call this one resistance for this particular conductor. This graph also shows if you reverse the current, it means if you change the polarity of the battery, make this one positive and make this one negative, the current will reverse and it still form a linear relationship. If you plot this one, V equal to Ri or IR, if you consider this is your Y, this is your X, so the slope is the resistance. And in here, in this plotting, we can always find the gradient or find the slope. And this one M is equal to R, and this is how much change over how much change. In terms of the unit, resistance is V over A. It means volt per ampere, and ohm is a preferred name for volt per ampere. Now, however, not all materials they obey Ohm's law. So Ohm's law, in a way, is not like a universal law, like a Newton's law of universal gravitation. It's not at this level. Not all the material obeyed. So if we find most likely a conductor obey the Ohm's law. However, electrical and electronic engineers, when they do the plotting, they like to reverse the X and Y. So what I mean is, if you look at the first plot we have, if we plot V versus I, and Ohm's law of V Ri, this is y, this is x, and this is your slope. However, if we reverse the plot like here, I versus v, it means the slope here will become 1 over r. It means compare with 1, compare with 2. In these two cases, the resistance for 1 actually is higher than the resistance for 2 because the slope is 1 over r. Look at the current versus V graph for the tungsten filament. This is what typically you will find for the light bulb. You will find for the low current, this is roughly about this. This is the resistance. But when the current increases up to here, can you see the slope become lower? So the slope lower, it means at this point, if we say this is 1, this is 2. The 2 actually has higher resistance than 1 because the slope is lower. Remember, they are reversed now. So what it means is when the tungsten filament, if you're putting too high a current in, the temperature increases, and this increases of temperature will in terms increase the resistance or the resistivity of the tungsten. There's another type of material is another way around. When you have a low current and compare with high current, which resistance higher? If it is R1, R2. In this case, when the current is higher, the resistance actually is lower. Remember, the resistance is inversely proportional to the slope. Here, this is another type of material, and this is not a single material. This is called PN junction. It's a very complicated semiconductor and modified by a impurities. Now, if we put a positive current, it means if we push the current from one side here, if we say this is positive, we'll see here. And in the beginning, the resistance is very high, so the slope is very low. And then suddenly the resistance becomes very low. When you reverse the current, it means when you push the current from here, this is called positive current, this is called negative current. It just blocks. There's no way you can push the current from the other side. So this is we call a diode. So you can see if the material, most likely metal, they obey the Ohm's law, we call this type of material ohmic. And if the material doesn't obey Ohm's law, say tungsten filament, when the current become very high, or thermistor, in this case, or diode, we call this non-ohmic. From the definition of electric potential, V equal to delta U over delta Q. So it means when you have charge start from the positive and all the way through here, the amount of energy it delivers per unit charge is V. So the total energy it delivers is U V over delta Q. And by definition, the power is equal to delta U, delta T. It means this is in joule, this is in second. Each second, how much energy deliver or transfer from one to the other. Remember, U can be written as V over delta Q. So we replace the U by V delta Q. We regroup delta Q over delta T. It means how each second, how much charge passing through a specific point. So this is delta Q, delta T, and this is our electric current. If you know the voltage of your battery, V, and if you measure the current and the power of the battery delivered to the outside is VI, and the unit is joule per second or watt. If the load of the circuit is R, because Ohm's law, V equal to IR, so the power P become VI, and now we substitute this one back here, and it is IR I, therefore I square R. Alternatively, we will say P equal to VI, but this time we say from the Ohm's law, I is V over R. So V, and by Ohm's law is V over R. Therefore, power also can be written as V squared over R. When we talk about the resistance of a resistor, we specifically mean this resistor. This particular resistor we measure, for example, here, this is a resistor, and now we measure the current. And this is the battery, and connect to here. At the same time, we measure the voltage. So the resistance of this specific resistor is R equal to V over I. However, one can ask this question: what if we change the length of this specific material, or change the area of this specific material, and we measure the resistance again? So what happened? If someone double the length of this particular resistor, they will find the resistance is also double. So R is proportional to the L, the length of this resistor. We also found if we increase the area, say if we double the area, the resistance actually reduced to a half. So the resistance is proportional to 1 over A. Now we can write these two proportional observations into one, which is R proportional to L over A. Now this is a proportional sign. So mathematically, if we want to put this proportional sign into an equation, we need to introduce a proportional constant. So this is called resistivity of these materials. So let's summarize what we have. We know now when we do the resistance measurement of a specific resistor, there's two factors. One is called external geometry, which is the length and the cross-sectional area. The other is the intrinsic property of the material. We call this resistivity. So we combine all this, we can write now the R resistance depends on the external geometrical factor, which is L over A, and also depends on the specific type of material you choose. So this is resistivity. What is the unit of resistivity? Let's look at how resistance relates to L over A and resistivity. Now we do some algebra. We put resistivity as the subject of this equation. So it becomes R A over L. And now we ask, what is the unit of resistivity? This is the unit of R multiply the unit of area and the unit of length. The unit of R is ohms. The unit of area we use meter square. The unit of length is meter. So the unit for the resistivity is ohm meter. Here is a table showing the resistivities of some common material. You can see from here roughly to here, the resistivity is about -8, -7, -8, or pure carbon -5. This is actually graphite. The unit is ohm meter. Now if you look at the other extreme, this group, and their resistivity is 10 to the power 17, 10 to the power 15, 13, 14, so it's very high. Therefore, when the resistivity high, they are insulator. When the resistivity is low, they are conductor. And you can see here, there's two materials. This resistivity is roughly sitting in between, so we call this semiconductor. We just learned for a specific resistor, its resistance is proportional to the length L and inversely proportional to the area. The proportional constant is rho. This is the material dependence. It means it depends on which material you use. And this is the equation showing how resistance depends on the material properties and also depends on the geometrical properties. Now we can extend our investigation and ask this question. If the resistance depends on the temperature, so we can change the temperature of the environment and do the resistance measurement again, what we find is the resistance does change. It means the resistance depends on the temperature. Now, because L and A, they are geometrical factor. So what it really means is the resistivity depends on temperature. Now imagine we perform this experiment. Here, this is the table. This is the temperature. And this is resistivity. At temperature T0, it can be any temperature. You measure the resistance and then you use the LA and calculate its resistivity. Next, you increase the temperature to T and you will find the resistance also change, and then the corresponding resistivity also change. Now if the change, it means rho minus rho naught, the final minus initial, is proportional to T minus T naught. Again, we can set up an equation and include a proportional constant. This time, we call this constant alpha. So let's do some mathematics. Rho equal to, this is negative, so we put it here, rho naught plus alpha T minus T naught. So this equation tells you what is the value of new resistivity at temperature T. And remember, this is only an approximation, because when we extend the range of the temperature, very often we'll find it's not really linear. It will also change depending on different type of materials, and we're going to look at it later. Let's use copper as an example. At 20 degrees, the resistivity of copper, rho, is equal to 1.68 times 10 to the minus 8 ohm meter. At 100 degrees Celsius, the resistivity of copper increases to 2.23 times 10 to the minus 8 ohm meter. So first we find the change in resistivity. Whenever we talk about the change, it is always the final minus the initial. So this is 2.23 times 10 to the minus 8 ohm meter minus 1.68 times 10 to the minus 8 ohm meter. Now we find the fractional change. So the numerator is the change, but if we over this one by the original 1.68 times 10 to the minus 8 ohm meter, we call this factor fractional change. Now for the fractional change, if you look at the unit, the numerator is ohm meter, but the denominator also ohm meter. So what I mean is the fractional change, it doesn't have any unit, it's a ratio. Now we calculate per temperature change. It means we over all this value by the change in temperature. It means 100 degrees Celsius minus 20 degrees Celsius. So the number you will find in this case is 0.00393 per Celsius. This is what we define alpha. You may remember earlier we found the rho equal to rho naught 1 plus alpha. Alpha is our temperature coefficient of resistance, T minus T naught. So rho minus rho naught, the change is equal to, so rho equal to rho naught minus rho alpha T minus T naught. This is positive. And then rho minus rho naught equal to rho alpha T minus T naught. Therefore alpha equal to rho minus rho naught over rho per T minus T naught. This is exactly what we learned. Now if this is positive, it means just like copper, when the temperature increases, the resistivity increases. So let's see how you should answer it. For most conductors, such as metals, the temperature coefficient of resistance is positive. This means when temperature increases, the resistivity of the conductor increases. This happens because as temperature rises, the atoms in a metal vibrate more, making it harder for electrons to flow, thus increasing resistivity. Let's look at, there are some material, especially semiconductor, the temperature coefficient of resistivity is negative. Now let's see what happens. Now we start again. Rho is equal to rho naught 1 plus alpha. This is our temperature coefficient, T minus T naught. And after the rearrangement, we know alpha is written as rho minus rho naught, the change in resistivity, but this is a fractional change. And then we are looking at per unit of temperature rise. If this coefficient is a negative, what it means is when the temperature increases, final minus initial, the resistivity actually decreases. Therefore, this number here will become a negative. So for semiconductors, the temperature coefficient of resistivity is negative. This means when the temperature increases, the resistivity of semiconductors decreases. In semiconductors, increasing temperatures provide more energy to break bonds and release more charge carriers. The charge carriers in semiconductor can be electrons and holes, so it's very different from metal, making it easier for current to flow and decreasing resistivity. Let's look at this exercise. We start with rho equal to rho naught, the original, 1 plus alpha, the coefficient of resistivity, T minus T naught. And the original is 1.68 times 10 to the minus 8. 1 plus the alpha is 0.0039 per Celsius. And how much change? 40 minus 20. Final minus initial. And you will find the final resistivity is 1.81 times 10 to the minus 8. Remember, it's ohm meter. So when the temperature increases from 20 to 40 degrees, the resistivity increases from 1.68 times minus 8 ohm meter to 1.81 times 10 to the minus 8 ohm meter. Therefore, again, the temperature coefficient is positive. Let's look at the case for semiconductor. Now, rho is equal to rho naught, 1 plus alpha, T minus T naught. And the rho is equal to, at 20 degrees, 6.4 times 10 to the power 2. 6.40 times 10 to the power 2. 1 plus the temperature coefficient. This time is negative 0.075. And the change in temperature, final temperature 30 degrees minus initial temperature. And you will find this is equal to 160 ohm meter, or of course 1.60 times 10 to the power 2. So what happens is at 20 degrees, if it increases to 30 degrees, the resistivity of this semiconductor starts from 6.40 times 10 to the power 2 ohm meter will change to 1.60 times 10 to the power 2 ohm meter. It means it reduces. Therefore, the temperature coefficient for semiconductor is a negative number. Our next topic is circuit configuration. Let's first learn some key terms which describe the circuit. First is nodes, and also some people say junction is the same meaning. A node is a connection point. Here we have 1, 2. It means this point and the second point connect the resistor. We have another point here. It connects these 2 points, has a resistor in between. Of course, we have this one, so there's another resistors. So we have a 1, 2, 3, 4. How about the battery? Yes, the battery also connect by these 2 points. So in this example, there are 1, 2, 3, 4, 4 nodes or 4 junctions. Next, branches or path. A branch contains one or more circuit elements connect between 2 nodes. So let's look at it. We have first branch or first path, which is the battery between this and this node. we have second branch or second path, which is the resistor between this and this, and so on, this one, this, and this. So in this circuit, there are 5 different branches. Next is loops or closed circuits. A loop is a closed path through a circuit. And here, there's a first, second, and the third. So in this example, there are totally 3 loops. So we have 4 nodes, 5 branches, 3 loops. Now, there's a formula. Here, the B is the branches. So branches is 5. N is the node 4. So 5 minus 4 plus 1. And equal to 2. What I mean is 2 is the independent loops. Now, we may say we have total 3 loops. But the important thing is the 3 loops, they may not be independent. So the idea is how many independent loops. And in this example, or if you count the number of branches and the node correctly, it will show you there's only 2 independent loops. We want you to identify and count the number of node branches and loops in the circuit. And also I want you to mark it. First, there are how many nodes? 1, 2. Now, don't forget, between the battery and the resistor, this is N, then the node. So N equal to 3. Branches is between 2 nodes. So we have 1, 2, 3, 4. So we have 4 branches. B equal to 4. So next is number of loops. Is a closed loop. So here, the first one, the second one, and of course the third one. So the loop is 3. Now let's check with our equation. The equation say L, the independent loops, equal to B minus N plus 1. So B is 4 minus 3 plus 1. So again, there's a 2. There are only 2 independent loops, but we have 3 total loops, so it is okay. Now there are 4 circuits here. They appear different at the first glance. However, we want you to look into the detail and determine whether they are really different or they actually may be equivalent. So we want to first identify the node, branches, and the loops and see how they are. So let's look at the nodes. Circuit A, there's a 1, 2. So for circuit A, N equal to 2. For circuit B, 1, 2. So N equal to 2. For circuit B, or for circuit C, 1, 2. So N equal to 2. Circuit D, 1, 2. Now remember here, there's a no node here, so there are only 2. Next, let's look at the branches. Circuit A, 1, 2, 3. So the branches, 3. Circuit B, 1, 2, 3. So the branches also 3. How about C? 1, 2, 3. How about D? 1, 2, 3. So also 3. Now let's look at the loops. Here we have 1, 2, 3. So L equal to 3. Here we have 1, 2, 3. Number C, we have 1, 2, 3. And here, of course, 1, 2, 3. So they are all have 2 nodes, 3 branches, and 3 loops. They may be still different now, but you can see they are same. Now I want to redraw all the circuit, so to convince you they are actually the same. A, because you have 2 loops, so I can actually reshape this circuit and put this circuit here. Now this one, because this branch here, I can flip this one to the other side. Okay. Now this, if you look at here, I can change a little bit, and this one become now this and this. So A and B actually the same. And you can see the C is exactly similar. If you look at here, the battery. Now the important thing is the load. The current here split into 2, return. So the current here split into 2 and then return. Okay. The same here, the current here at this node split into 2 and then through the 2 branches and then return. So this is also the same as this one. So it doesn't matter how we draw it, as long as all the circuits have the same number of nodes, same branches, and also same loops. They actually are the same. Here we have 2 resistors connected in series. Look at this point here and this point. These 2 nodes here, there is only 1 branch. 2 nodes, the beginning, the end of these 2 resistors, but there are only 1 branch. So they are connected in series. Now we want to find a so-called equivalent resistors. It means, can we replace these 2 resistors by 1 resistor? The answer is yes. So the value of this equivalent resistor, which RS, S here stands for series, you just add the 2 resistors. It means the R1 plus R2. In a series resistance, every point along here, they will have the same current. However, the voltage V1 and V2 will be different because I is the same, but the R can be different unless R1 equal to R2. In this special case, they are the same. Next, let's look at 2 resistors. They are connected in parallel. Now, this is a node. This is also a node. In this case, between these 2 nodes, there are 1 branch and 2 branch. And in this case, these 2 resistors, they are connected in parallel. So remember, when we draw this one, we draw this in parallel, but we can also draw it like this. So these two, they're also in parallel because there are two nodes and two branches. 1, 2. Okay, now we want to find one resistor which can replace these two resistors. So the way to find it is we can find it with the reciprocal formula. It means Rp reciprocal equal to R1 reciprocal plus R2 reciprocal, or you can write it in this form. Now, if you do the mathematics, you will find Rp is equal to R1 times R2 over R1 plus R2. The reason is simple, 1 over Rp, and you find the common denominator. This is R2, this is R2 plus R1, and then you flip, you find the inverse. Rp equal to R1, R2, R1 plus R2. Now, this is a formula a lot of engineers they like to use, and also this is the way they like to write the two resistors in parallel. There's one important point. When the two resistors they are in parallel, they will have a same common node. So it means the potential across R1 and the potential across R2 will be the same. However, the I, the current passing through R1 and the current passing through R2 will be different. Why? Because I1 is VR1 over R1, I2 is VR2 over R2. They will have the same with potential difference, but the R1 and R2 in general, they are different. And also one important point is the higher the R, if R2 bigger than R1, we can say I2 will be less than I1. So they share the same potential. The higher the resistance, the lower the current. So you can imagine, go to the extreme. Remember, when R2 become open circuit, it means infinitive. In this case, Rp, 1 over Rp equal to 1 over R1 plus 1 over infinitive. So this equal to roughly, or you can say this is 0. So the only R is R1. In this example, it asks you write down the equivalent resistance between A and B using engineering notation. So this is important. So I want you to think about R2 and R3, they are connected in parallel. So for the engineering notation, this is R2 parallel to R3. These two resistors, and then they are connected to R1 in series. So the way to write is this one. And we can say this is RAB. It means the resistance between A and B. This is what you can imagine when you use a digital multimeter. When you measure the resistance, that is, you can replace all three resistors by just one. B, if we plug this one in, we'll say RAB equal to R1 plus R2 parallel R3. R1 is 1K. Now, again, for engineers, they usually will drop the unit in the middle of calculation. But don't forget, you have to keep the prefix. So this is 1K plus, because they're in parallel. So this is 3K parallel 6K. and you will find, if you plug this one into the formula, use your calculator, you will find this one equal to 2K, and therefore you will find this is equal to 3K ohm. See, we do the same thing. R1 plus R2 parallel R3. R1 this time is 2K plus 4K parallel 12K, and this is 2K plus 3K, and the answer is 5K ohm. Now, because you're putting the answer here, you must write down the unit. Number 14, R1 and R2, they are connected in series. So you have R1 connected to R2 in series. And the bottom branch, you have the bottom branch. These two, they are connected in series. R3 plus R4. But you have this branch and this branch, they are connected in parallel. So we bracket this, the upper branch, the lower branch, and then they are in parallel. So this is your RAB. So what we can do now is plug the value 1K plus 2K parallel 2K plus 4K. Remember, this is very important. It is do the bracket first. So this is 3K parallel 6K, and the answer is 2K ohm. Part C, we do the same thing. RAB equal to R1 plus R2 bracket parallel R3 plus R4. This is 4 here, and this one is 2K plus 2K parallel 4K plus 8K, and we have 4K parallel 12K, and the answer is 3K ohm. Number 15. Now I want you to see this point, this node and this node, they are actually connected together, and you have another node. So this circuit, if you look at it, is actually like this. R1, R3. If I withdraw this one, they will be look like this. They are exactly the same, these two. So it is very clear now. R1 and R3, they are connected in parallel. So first R1 parallel R3, and also R2, R4, they are connected in parallel. And then you put the bracket. These two groups, the first group, second group, they connect in series. So this is your RAB. Number B, so RAB, I just plug the number now. This is 4K parallel 4K plus, beg your pardon, this is 3K, because this is R3, and this is 4K parallel 6K. So this is 1.71K plus 2.4K, and it is equal to 4.11K ohm. C, RAB is 1 is 6K parallel R3 4K plus 6K 12K. So this is 2.4K plus 4K and equal to 6.4K ohm. Here I want to introduce two very important laws. The first law called Kirchhoff current law, the second law called Kirchhoff voltage law. These two laws, they are important because very often a complicated circuit, you cannot reduce it into parallel or series connection. So you have to apply some laws which allow you to analyze it. The first law called Kirchhoff current law, and the idea is very simple. First, we have to identify a node, and it is all about nodes here. The law say you look at the current flowing into the node, and you look at the current flowing out to the node. The sum of all current flowing into the node is equal to the sum of all current flowing out of the node. So in this particular case, I1 flowing in, I2 in, I4 in, and also I5 in must equal to the sum of I3, which is out, plus I6, which is out. The basic idea is conservation of charge. The second law, this is Kirchhoff voltage law, KVL. This is a conservation of energy. Now the idea is that when the charge goes up a loop, the total energy is gained from the sources equal to the total energy it loses in the resistors or other elements. Now, let's look at it from the point of view of conservation of energy first. This is a resistor, or the same. Incidentally, the way I draw this one is we call European convention, and this is American and Australian convention. They are the same. They represent resistor. And it say if the current passing through here, it loses energy. So the potential difference is V equal to IR. But this time we have to use negative because it loses energy. When the current passing through a battery, say this is positive, negative, its potential energy actually gained, because this is how the battery convert the chemical energy into electrical potential energy. So this is positive here. So the idea of Kirchhoff law is you first find a closed loop. This is why we need to learn how to find the loop. And then we run across the loop. Whenever component we see, maybe this is a battery, maybe this is a resistor, we are asking how the energy goes up or come down. And then when we sum all these energies, they must equal to 0. So let's look at an example. This is example. We have a battery, and this is negative side, positive side. Incidentally, I also want to put this one as positive. It means a high potential, low potential, high potential, low potential. And it's so the current start from the positive terminal of the battery will pass through the high potential of R1, so it loses energy. And then from the high potential R2, it also loses a little bit energy. The same here, high potential, low potential, it loses energy. Once the charge return to the negative terminal of the battery. Inside the battery, it gains energy. So this is the energy diagram. From A, this is the negative terminal. The charge increases its electrical energy from 0 to 12 volt. Okay, so when it passes through R1, it reduces, it loses its energy. So this is how much energy it loses, delta V across R1, IR1. And during the conducting path, we assume there's a no energy loss. And then this is an energy loss across R2. The same, no energy loss between the connection of R2 and R3. And then it loses energy again once it crosses R3. So this is how energy loss R1, R2, and R3. Across the battery, it gains energy, positive 12. We skip it, it's joule per second, of course, volt. Across resistor 1, so remember, the energy is V equal to IR, and the R is 1 ohm, so it's 1 I. R2, 2 I. R3, 3 I. So the sum of these terms, positive, negative, 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 equal to 0. Simplify this expression, positive 12 minus 6I equal to 0. So I equal to 2 ampere. However, there's another convention which we usually call engineering convention, or some people will call it passive sign convention, PSC. They are the same. Now for the passive sign convention, so instead of focusing on the energy gain or loss, we focus on when the analyzing path enters the component, whether it enters from the high potential or low potential side. So let's see. Just this example, simple example. This is positive, negative. Now for the R here, this is high potential, this is low potential. So when you enter the R from the high potential, it becomes positive. So this time it is positive IR. When we analyze, follow the current, enter the battery. When we enter from the negative side, so here become minus V, and the sum of this one, it means positive IR plus negative V equal to 0. And you can see you will give the same answer because you just flip the sign from the previous convention. But I want you from now on stick to the engineering convention, or PSC, passive sign convention. Let's using the passive sign convention or engineering convention for the same question. Now, again, we have to mark the potential across each component. This is positive, this is positive, this is positive. And we analyze the loop following the current. Now we start from the battery. It entered the battery from the negative side, so this is negative 12. And then it entered the first resistor R1 from the positive side, so this is plus IR, so R is 1 I here. Same, this is positive 2 I, and same, this is because it enters the resistor from the positive potential side. So this is positive 3I. And KVL, Kirchhoff voltage law, say when you sum all these terms, they must equal to 0. So this is at least 1, 2, 3, 4. When you sum all the terms, 1, 2, 3, 4, they must equal to 0. And if you look at the mathematics, you will find that I is the same, 2 ampere. In this example, R2 and R3 are connected in parallel. And then this parallel pair is connected to R1 in series. First, step 1, check your understanding. This is check the topology. It means how many nodes. And we can say this is 1, 2. Remember, they are connected the same. So there are only 1, 2 here. But there's another one here, 3. There are 3 nodes. Label the KCL, okay? We find the KCL in one of the loop. Say in this case, we focus on this particular one. So the current is here going in. So we call this I. So we call this IR1. It's going in the loop, and the 2 current going out from the loop. One is IR2, the other is IR3. So the Kirchhoff current rule. So the Kirchhoff current law say flowing in IR1 equal to the sum of the current IR2 and IR3. They must equal. Step 3, what is the KVL? Now we can track the KVL. So now the first thing is choose the loop. So let's first choose this loop. This one here, and we find the positive and negative across each component. So they're already marked here. And let's analyze. When the current or when the direction of the loop enter the 12 volt, it enters from the negative side. So this negative 12 volt. The voltage across R1, we just call it VR1. This is positive because it enters from the positive side. Plus VR2, it enters from the positive side of R2. So within this loop, we call it loop 1. This is how we set up the Kirchhoff law. And by rearrangement, we say the voltage across R1 plus the voltage across R2 equal to 12 volt. We choose the loop 2 as the loop containing the R2 and R3, and we can choose how we analyze from the clockwise or anti-clockwise direction. We choose this time clockwise direction. Now it doesn't matter which direction we choose because we'll give the same answer. Now let's look at it. R2, because this time when we choose the way we analyze, we are coming to the R2 from the negative side. Now this analyzing loop doesn't have to be exactly follow the current. The current and the loop we choose to analyze, the KVL, can be different. So even though we know current flow through from here, but when we do the analyze, we can ignore it and we just choose this complete loop. And it enter R2 from the negative. And of course, this loop enter R3 from the positive. Therefore, we say negative VR2 equal to positive VR3. What I mean, the potential across R3 equal to the potential across R2, and it is really what we should know already. Okay, let's check using the usual Ohm's law or parallel series circuit. First, we combine these two together. So when R2 parallel R3, the equivalent is 2 ohm, because 2 is equal to 6 parallel 3. So this is 2. The total resistance. So we have to add this one. It means this circuit is R1 plus R2 parallel R3. The total resistance, this is 4 plus 6 parallel 3, and this is 4 plus 2 and 6 ohm. So these circuits can be reduced into just one resistor. This is the total, and this is 6 ohm. This is 12 volt. The total current is equal to, now the total current is the same as the current passing through R1. I hope you can identify, because this is the total current. There's no splitting, so when the current leaves the positive terminal of the battery, it's exactly the same when it enter or passing through R1. So therefore, I put this or this, they are the same. And use Ohm's law is equal to 12 volt over 6 ohm. So this is 2 amp. So when it start here, this is 2 amp, and when the current passing through R1, this is also 2 amp. However, you know, once the current reach the loop, it will split. Okay. Now next, we want to find the voltage drop across R1. So we call this one VR1. We know the current, we know the resistance. So the voltage drop is 2 amp, 4 ohm, 8 volt. But the total voltage is 12 volt. So if there are 8 volt drop across R1, the voltage drop across the parallel of R2 and R3 will be 12 minus 8 and 4 volt. So let's redraw this one a little bit better. So this is 8 volt. These two, they are connected in parallel, so they share the same voltage, and this is 4 volt. So we know R2, so we know this one, and this is 4 over 6 ohm. So the current passing R2 is 0.67 ampere. The same argument using Ohm's law, the current passing through R3 is 4 volt over 3 ohm. Okay, so can you see here, we already see the KCL work. It means the total current, the same as the current passing through R1, is equal to 2 amp. When it's split into two paths. One passing through R2, which is 0.67 amp. One passing through R3, which is 1.33, and you can see 2 amp equal to 0.67 amp plus 1.33 amp, and this is KCL. So this is exactly what we found here. Now how about the voltage? This is 8 volt, we just calculate, and this is 4 volt. So 12 volt when we enter this one. So put it this way, when we enter this one, this is from the negative. If we analyze this one, so minus 12 when this enter the R1 is positive 8 because it enter from the positive side. When it enter R2, again it enter from the positive side. Plus 4 equal to 0, and this is correct. So again, KVL is also true in this example. We just verify both KCL and KVL, they are correct. A, on your circuit diagram, using the plus and negative sign, locate the high or low potential. They are very important. So let's see. Positive, negative, positive, negative, positive, negative, positive, negative. Label all the nodes in the circuit. We can say it depends on how you choose. We have 3 nodes, and so we can say this is A, B, and this is C. It doesn't really matter how you label them, as long as you know there are 3 nodes. Next, how many distinct nodes are present in this circuit? Of course, 3. We just say 1, 2, 3. Starting from the positive terminal of the battery, trace the total current as it leaves the battery and passing through R1. Okay, so this is here. Describe what happened to this current when you write and loop B. Okay, apparently this question have to make this one A, B, C, and when it reach loop B, this is IR1, and this is IR3, and this is IR2. So the number B here, I will say IR1 equal to IR2 plus IR3. This is at node B. So we have to be very careful and specify which node. Part C, we choose the first loop here. This is loop 1. And we first look at how the loop enters the battery. It enters the battery from the negative terminal. So this is minus 27. And then it enters R1 from the positive terminal. So this is plus V over R1. Plus it enters R2 from the positive side. So V R2 equal to 0. Next, look at the loop 2. The second loop, we call it loop 2. Now remember, this loop is the loop we choose to analyze the circuit. These loops, it doesn't have to be the same direction of the current. So for example, here, we know the current passing through R2 from positive to negative. R2, but we don't need to follow the current because the loop we choose is this way. So we just look at when we follow the loop, when it enters R2, it enters from the negative side. So the voltage here, V R2 must be negative, but VR3 is positive. So this is 1, 2, three equations, and once we substitute all the value we know, we will solve all the unknown based on which one we know or which one we don't. Using Ohm's law, calculate the voltage across and prove the KCL and KVL. Okay, so again, the total resistance is R1 plus R2 parallel R3. So R1 is 5 plus 6 parallel 12. So it's 5 plus, this is 4, so this is 9 ohm. So this circuit can be reduced into this simple circuit. This is R total. This is 27 volt. So the I total, the current leaving the positive side of the 27 volt battery, is I total, and is equal to, of course, V over R. This is the total, and this is 27 over 9. This is 3 ampere. So 3 ampere leave the positive terminal of the battery. Of course, it will be the same as it which R1. So this is 3 amp. It means this is also 3 amp. Now, what is the voltage across R1? So let's calculate. VR1 is IR, 3 times 5, so it's a 15 volt. So the voltage now across R2 and R3. Okay, so the voltage across R2 equal to the voltage across R3, and it is equal to 27 minus 15 volt. So this is 12 volt. And the current passing through the R2 and R3, because now we find the V over R2, we find the V over R3. So the IR2 is V across R2 divided by R2. Ohm's law again. And this is 12 over 6, and this is 2 ampere. I are passing through R3, which is VR3. VR3 is equal to same 12, but the resistance is 12, so this is 1 ampere. So now let's verify and check the KCL. This is 3, and this is this is 2, and this is 1 ampere. So yes, KCL is true. It means the I enter R1 equal to the I leave the load. It means the sum of these two, 3 equal to 1 plus 2. Okay, KVL, we can analyze this loop, and we can say now the voltage across here is negative 27. The voltage across R1 is positive 15, and the voltage across R2 is positive 12. So the sum is equal to 0. So this is the KVL for loop 1. Now, of course, the KVL for loop 2 is exactly the same. And the KCL for loop 3 also work all the 3 loops. So these 2 examples demonstrate what it means of KCL and KVL.